So hello everyone. Thanks to Peter and Nate for the invitation. I did get this invitation on Monday, and so today is Wednesday, right? So I had a day essentially to prepare, and I didn't prepare any slides. It's going to be a talk, and it's just going to be kind of an overview of the things I've been working on in the past 25 years. It's kind of scary how time flies. So I started this work in 1999. Or actually 1998-ish. And so Nate just talked about the data plane. I'm going to talk about the control plane, okay? And at the end, one of the open problems I'm going to talk about is how do we bring these two theoretical sort of frameworks together, which is still an open question, I think, and an interesting one. But just to make sure everybody knows what I'm talking about, so Nate was talking about forwarding tables. They sit on routers, okay? And back in the olden days when the internet was very young, people populated these forwarding tables by hand. The internet was very small, maybe a couple dozen nodes, and network managers would talk to each other on the telephone and say, you know, here's how we want to configure the network, and here's how we want a path from Stanford to Edinburgh, for example. And they would populate these tables by hand. And then as the network grew, of course, they developed routing protocols, and these routing protocols run on routers. They talk to each other, okay, and they automatically populate the forwarding tables, okay? And so the initial idea of there was lots of theory, right? Dijkstra's algorithm, Bellman-Ford, shortest paths. And of course, the first protocols were based on that theory that everybody knew and has been known since the 50s, basically. And everything was fine. And then the internet grew and grew, and what happened is the network engineers and operators would talk to the vendors and sort of add tweaks to these protocols for solving this problem and that problem. And there in the IETF, the Internet Engineering Task Force, there were standardizations of these routing protocols, and they would change the specifications and so on. But then what happened is in the mid-90s, the internet was commercialized, and suddenly the way of connecting networks together, now we're going to connect commercial enterprises together, especially I'm thinking about backbone providers or transit providers. We're going to connect them together, and what happened there was basically they hacked something up that seemed to work pretty well, and it's called the Border Gateway Protocol, and it's still with us today. It's been probably one of the most successful routing protocols. In some sense, it's a very simple protocol. It's a distributed Bellman-Ford kind of protocol, and I'll talk about what these things are in a bit. But I got interested in about 1998, 1999 when I was at Bell Labs, because there were some anomalies. There's some papers on potential anomalies and potential solutions to these anomalies that could be seen in BGP. And I'll talk about these anomalies in a bit, but the basic proposal at the time was to sort of suck in all the config files from routers and then analyze them to see if these anomalies or things that could cause these anomalies were present. And the first thing I did with Gordon Wilfong and then with Bruce Shepard at Bell Labs was come up with a model, a sort of a really abstract semantics of BGP that we could actually prove theorems about. And we call that the stable path problem, which is SPP, not the SPP you just heard about. But basically, the stable path problem is this. You have a network. Every node is its own private list of how it prefers paths. And, you know, some paths it doesn't allow at all, and other paths it prefers over other, you know. So you have each node has a list. And then that's the problem. And what is the solution? A solution is essentially an assignment of paths so that no one can change their mind, given that their neighbor has In other words, given what their neighbor has, no one can change their mind. So it's a Nash equilibrium of some kind. And that's the problem. That's the stable paths problem. Very simple problem. You can start proving things about it. By the way, at the time, we were at Bell Labs. Of course, we went down the hall and talked to the people that do game theory, because we're talking about Nash equilibrium. There's no stochastic component to the stable paths problem or to BGP. And so they basically just said, well, that's mere combinatorics. Get out of my office. So anyway, so then we proved, for example, that showing that these anomalies are present you can't do it. It's intractable. And then we went off and, so I did some work at Bell Labs, and then they said to me at Bell Labs, yeah, stop doing that BGP work. We want you to work on this other project, this Death March over here. And I said, no way. And I hopped over to AT&T Research at that time. I said goodbye, and really it was the best move I could have made, because AT&T was at the time junking all of its telco equipment and rebuilding its entire network on internet equipment, okay? And BGP was the big problem that they had, configuring this protocol. So I was there for a couple of years, and I had an enormous amount of fun with a group there under Albert Greenberg, and Jennifer Rexford was there, and lots of really fun people. And we built a lot of tools for the network operators. We sucked in, we were just working mostly on the North American backbone, and we would suck in like 4,000 routers, config files. And typically the BGP configuration was about 2,000 or 3,000 lines of code in these things. And then we would essentially, we had a website where the network engineers could see that, oh, there was a discord between the way this router was configured and the way that one was configured. Really low-level stuff. I mean, really easy stuff to do in a lot of ways. But it was really great, because we got to learn a lot about how these networks were configured and the different interactions that they had with other routing protocols. So BGP is a routing protocol that's between service providers. Think of it that way. The global routing protocol that glues together the entire global internet. And then internally, there can be other routing protocols, typically based on shortest paths, more or less. I say more or less because shortest path with lots of engineering tweaks. I'm thinking of OSPF and ISAS. They have lots of engineering tweaks. And part of the interesting thing is the interaction of these protocols. So yeah.
BGP is also being used internally?
Yeah, I was going to get to that. So in data centers, for example, BGP today is like, it seems to be like very commonly used in data centers as the internal routing, as a replacement for a shortest path-based protocol. And I'll sort of indicate why that's happening in a bit. But so the kind of work I did at AT&T with a group of other people was, we did a lot of measurement stuff, just to look at the dynamics of the protocol. We built simulators to simulate the dynamics of the protocol. That was really interesting. We found lots of anomalies in the network and published papers about those. But more and more I became interested in sort of static semantics, trying to come up with ways of analyzing the network configuration. These were, again, very large configurations. And we built a tool at AT&T. This was, again, a big project. We called it the what-if-atron, because basically the idea was to suck in all the config files of BGP, OSPF, all sorts of even layer 2 stuff. So this is layer 2, I mean the sort of Ethernet kind of stuff that's underneath, or the whatever layer 2 protocols there are. And we would try to say, okay, what would happen if we changed the configuration? In other words, in OSPF, in the shortest path, if we increase the length of this link, what would happen to the routing? And then we'd try to simulate that and look at it. And then we'd actually, because we knew what was going to happen in the network, we talked to the engineers, and then we would see, oh yeah, does our what-if-atron predict exactly what is going to happen? And, we got pretty close. Yeah, Peter?
So is this, it was simulating data plane connectivity, or also even the amount of traffic that was trying to get from A to B yesterday?
So that's a good question. That's a good question because both were involved, but it's a very good question to remind people that internet routing protocols do not care about traffic. Okay? They are perfectly happy to route all the traffic in the internet through the tiniest link. It all has to do with configuration. So internet routing protocols do not route around congestion, period. What's happened is that routing around congestion is at network management timescales, not at the millisecond timescales of routing protocols. So if network managers see that some link is overloaded, right, what they will do is, that's why we need a what-if-tron. They will say, okay, I want to shift some of that traffic, and I'm going to change the OSPF weights. And so this kind of thing happens at timescales of days and weeks of measurement. And the reason this is done is because people learned very early on in the internet that if you try to route around congestion, you introduce oscillation in the network, because any control plane is much slower than things happening in the data plane. And you just get this feedback loop, and it's horrendous. Nobody's figured out how to do that properly, okay? So it's a good question, but that's the reason why we want a what-if-tron, is that we want to be able to predict how traffic will be reestablished, how a stable routing will be reestablished after BGP policy changes or OSPF policy changes and so on. So what you really need is a semantics of these protocols, right? And we worked a lot on that. It was complicated because you can't just read the spec, the IETF, right? You've got to actually look at what's happening with a particular vendor. And not only that, but at the time, AT&T was all Cisco, but it would depend on the release, the version release of the Cisco code, how it behaved actually. And so our what-if-tron had a big case statement, are you on version this and version that, and so on. Shanker.
Failure and resilience to failure.
Well, that was another thing the what-if-tron was supposed to do, is like, I should say that one of the things that you do in a big network is you want to reconfigure, you want to bring, at least every week, you want to bring, each router has to get rebooted like once a week, or once every 2 weeks or so. And so you want to bring it down, reconfigure it, reboot it, bring it back up. But you can just turn it off, right? And they used to do that. But then what they did is they discovered a way of slowly increasing the OSPF weights of going into the router until no traffic is going through the router any longer, and then bring it down. So that's another thing we wanted to simulate with the what-if-tron is, well, okay, let's do that to that router. What's going to happen? Notice I say router and router. I can't decide which continent I'm in. So anyway, the research work I did at the time, a lot of it with Gordon Wilfong and some other people, was trying to abstract away a bit from the network, and we used the SPP to prove interesting things about BGP, because BGP has all sorts of weird stuff in it, like route reflectors and multi-exit discriminators and weird things that can happen. And we used the SPP model to analyze those things and show that things that the designers of BGP claimed could never ever happen, can happen indeed. For example, the BGP designers say, on a stable routing of BGP, you cannot have routing loops. Forwarding loops, I should say. And that's false. And actually, we saw that happen at AT&T. Now, I'm going to talk about the anomalies, okay? And the anomalies that can happen in BGP are two, really. I mean, the ones we focused on. There are many other things that can happen. But the ones we focused on, it's possible for BGP not to converge, okay? In other words, it just chunks along forever. exchanging routes and never comes up with a stable path. And the other problem is that there can actually be multiple stable states in the system. Okay, so a stable path problem can have 0 solutions, in which case you don't converge. It can have multiple solutions. There's no guarantee that BGP will find any of them. Okay? And the problem with multiple solutions, and again, this is something that we saw at AT&T. Actually, a sort of a network operator came into me one day and said, this simulator is broken. It's got a bug in it because I'm trying to simulate the network and it diverges. This was OpNet, I think it was called at the time, very expensive simulator that they bought. And it took me a couple of months to figure out what was going on. Basically, the problem of multiple solutions is you have you have somebody here and somebody there. This guy prefers the path through that way, and this guy prefers the path through that way. Okay, and what happens is that because because the simulator was a lockstep thing, just fired everybody simultaneously. Of course, you can't solve this, but in the real world, you fall into one or the other. Right, because of all the asynchronous computations that's going on. You fall into one solution or the other. And the problem with the particular thing that was happening, this was essentially Europe, and this was North America. I'm really simplifying this. And there were many, many, many routers in these paths. And the problem was they were sending what's called BGP communities, little tags, that travel along the routes and influence the policy at a distant location. And they were using those. And they came up with this thing where the system gets wedged into one solution or the other. And I wrote an RFC on this, and we called these things BGP wedgies, which was a lot of fun. And I would give talks to the network engineers about this, and they would say, how do you know when you have a wedgie? And I would say, oh, you know. And it was, you gotta have fun, right? So anyway, this actually happens, by the way. And the thing, oh, there's something really important I forgot to tell you. Suppose this is a network. Let's say BT. This is AT&T. Maybe this is another network, China Telecom, I don't know. They do not share their policies. Their policies are proprietary, right? Because they reveal a lot about how you're treating your customers and who are your customers. I mean, you can find out in other ways, but there's a lot of proprietary information in these config files. So the thing is, how do you debug a problem like this? When, in order to debug it, you have to have global knowledge, but the configs aren't shared. Now, when I show this kind of thing to the designers of BGP, when I went to Cisco and showed them this, they say, well, that's misconfiguration. But what does that mean when people don't share? No one has a global view. What does it mean to be misconfigured? This is a protocol bug, okay? And so, yeah.
You talked about the network management thing taking place in sort of days, weeks.
Yeah.
What kind of timescale are these things sort of supposed to stabilize?
Well, they stabilize, BGP timescales, which is, when you change in the global internet, when you make a change, how long does it take for the global internet to stabilize? And there's been a lot of measurements done on that, and sometimes it depends on the scope, how widely visible is that prefix, okay? But it can take from anywhere from a few seconds to 20 minutes. Probably longer now. That statistic is a little bit outdated, but yeah.
So talking about stability doesn't make any sense.
Yeah.
Right. Okay.
So people initially I was inspired by the problem of divergence, like never converging, but I actually think this is more insidious. Because the never converging did happen with a weird interaction with what's called a multi-exit discriminator, and we did some analysis on that using the SPP. Basically what's happening with the multi-exit discriminator is they've introduced an order on routes, a sort of preference order that's not transitive. And so how can any network operator understand a non-transitive, a non-transitive, well, I could spend an hour talking about MED, but I won't. Okay? So that's actually where non-convergence has happened in practice. It tends not to happen in the global intranet because of the way that you prefer customer routes over provider routes, and in between are peer routes, your competitors that you want to share routes with. So there's a natural, because of the way money flows in the internet, there's a natural way to order. I'm not saying that this isn't violated on occasion, it is, but there is a natural way to order things. And Jennifer Rexford showed that when that's true, then, well, you can actually use the SPP. She didn't use the SPP for that, but you can. You can show that when you use that ordering, the sort of the natural one imposed by economics, that you get stability on the global internet. But you don't necessarily avoid these kind of wedgies, okay? And these kind of wedgies are there, and they happen, and basically the network operators really don't understand what's happening. Yeah.
When you say things, when you say it doesn't converge,
yeah.
Does that mean while it's not converging, things route in unstable ways, or things just?
Yep. No, you'll get back and forth, back and forth. Packets can get lost in internet forwarding loops. Bad things happen. Yeah, very bad things happen. Anyway, so why does all of this happen? Let's take a look. Here I am. Let's think about shortest paths first. Okay, we're here. We have a neighbor, another neighbor, and here we have our destination way over here. And let's say in the routing protocol, this has weight A, this has weight B, and this has weight C, and this has weight E. Okay, this is the destination D. Okay. What makes things like shortest path work, right, is that, by the way, I'm just going to use, this notation. I'm going to think about semi-rings as being a sort of a generalization of shortest path. So, for example, min plus finds shortest paths. Max min finds highest capacity paths. Okay. So algorithms like Dijkstra, Bellman, Ford, and so on can be generalized to semi-rings that have certain properties. Not all semi-rings, of course, but if you have certain properties, in particular, I mean, what's really happening here? You want to make sure that A is always, this is a root in S, okay? A is always less than or equal to B times A. So times is the thing that you're going along a path. And semi-rings are like rings, except this guy is not a group. You don't have inverses, okay? And the whole thing works exactly because of that fact. You can use these semi-rings to find paths, best paths, as long as this thing doesn't have inverses. And so as long as it's sort of increasing in this way, in other words, you never get a better path when you extend it, okay? So this is going to be the key thing. Now, the other thing that works in BGP land, in semi-ring land is, A times B plus C is equal to AB. This is times here, I'll just to be explicit. Plus A times C, okay? This is distributivity. This is just the left version of distributivity. And this is kind of, if you look at all of the theory books on semi-rings and Gondran and Minot, for example, this is the key equation, and the right version of this are the key equations that are used for all of the theory that's developed there for semirings. So the thing about it is, this guy has to make a decision, okay, about which path is best, okay? So what does this mean, right? This guy means that, you know, did I do this properly? Let's see. Yeah. Plus, yeah. So let's take a look at this, right? This is kind of global knowledge. You know, if I'm sitting here, here I am, this is me. If I have global knowledge, I can say, okay, I'll pick the best path, right? This one, you know, I've actually drawn this incorrectly. This is not the right diagram, sorry. No wonder I'm confusing myself. How could I forget this? This is my neighbor. Here I am. This is me. I have a link of weight A, okay? This is me making a decision with global knowledge. This is my neighbor making a decision here, okay? And passing the result to me, and then I get what my neighbor gives me, okay? So in BGP land, this is not true, okay? Why? Well, the thing is, for example, suppose this is a path through a customer, and it's really long, a long path. And this is a path through a competitor, okay? This guy is always going to prefer its customer. That's what the customers are paying them for, connectivity to the internet. I mean, imagine this customer calling up and saying, why aren't you using the route I'm sending you? Well, my competitor has a shorter route. Oh, okay, I'll move to your competitor now. Thank you very much for your services. You know, so you prefer customer routes no matter what. So this is a short route, let's say, and BGP breaks ties on the length of the path, okay? So this is a short route. This is a long route from a customer. This guy prefers that way. If I had global knowledge, well, I'm a customer of, this is my provider, upstream provider. So all routes from my upstream provider look the same, essentially. You know, I'm just going to pick the one with the shortest path. So if I had my druthers, I would go this way. Okay, if I had global knowledge. I won't have global knowledge because in BGP land, I'm stuck with this solution. In other words, again, given what my neighbors have, I get the best thing I can get. You know, sort of the SBP idea, you know, Nash equilibrium kind of thing. Okay, so that's why BGP breaks this distributivity rule, okay? Because it's based on economics. And, you know, I've talked to Yakov Rector, who's the designer of BGP, and I said, you know, I tell him this kind of thing. He says, no, BGP is based on shortest paths. You know, we've got this path that we keep track of, and I, you know, I have to convince them that actually you're doing something different here, Yakov. But it's sort of related to your question, Nick, before about what the hardware vendors and vendors, how do they think about this stuff? They just want to solve customer problems. They never think about the network-wide implications of their design choices. Never. I've talked to these, I mean, at least the ones I've talked to. They're just interested, they go out to customers and they hack BGP, they add new attributes, they do things to solve this problem here, okay? And how that affects the global network, they never think about it. I mean, we wrote an RFC on this. The vendor group has systematically ignored it. They just they don't want to deal with it. That's my impression. Yeah.
So you're telling the kind of intellectual history. The SBP paper is one of my favorites, and people should read it if they haven't. But as you say, it sort of didn't have a it didn't have a sort of semantics, like sorry, gives the semantics to BGP, but without any syntax or any.
Yeah.
So, and obviously, semi rings and graph problems, that they go hand in hand. People have done it for a long time. But when did you start to make the move to?
Thank you for asking that. I'll get on that right now because I was at AT&T and I was sort of seduced by all of this data and stuff, and it was a lot of fun. But then I left AT&T when the roof started collapsing, and so I went to Intel here in Cambridge, spent about a year there, and then moved to the computer lab in 2005. Okay, and at that time, I sort of moved away from having my hands on all of this data, and I started thinking about which direction to take here, because we'd already done all of this what-if-atron stuff, and I remember talking to Peter about this, and one avenue that I could have taken, and I didn't, was to sort of, kind of inspired by Peter's analysis of TCP, is sort of to look at these protocols really closely and try to formalize them and reason about them and this and that, and to then reason about large configurations of actual real Cisco routers or Juniper routers and things like that. I mean, I sort of played a little bit for a year and a half with that kind of approach, and I decided that it was not for me. I was not emotionally well suited for that kind of work. So what I decided to do instead was, the original routing protocols were based on a well-known theory of shortest paths. So I wanted to come up with the theory that these new protocols should have been based on had it been available. Okay? And why do that? Hold on a second. Why do that? Because I'm thinking about the future, because we want to develop new protocols. I'm also thinking about other fields, not just networking, right? Because this kind of thing, I think, arises in a lot of different fields, maybe in finance, maybe in various kinds of optimization steps. I'm talking about this inequality here. And I want this work to be applicable in other areas, and I want to go out to people, and I've done some of this already. I want to go out to people that are not in the networking community. Essentially, we want to start from the semi-ring world. So here's semi-ring world, and we want to sort of expand that to these kind of weird exotic algebras, let's say. Now that's what I started doing, and so because I just think that trying to formally specify these protocols and keep up with all the changes. I mean, the IETF is just churning out changes all the time, Peter.
Mark in a foolhardy way on nail down BGP. Would that have been possible?
Maybe, but I'm not sure. Like I said, I just didn't want to do it. I mean, one could do that, and I think maybe it's helpful to do that in certain cases where you want to reason about your network. Yeah.
So had a project doing this a few years ago. We published it, I think, eventually backed by the media system, and so they went laboriously through the BRFC and built a Coq model and proved some theorems using their Coq mechanization of BRFC. They even found, I believe, small sort of gap in the Gauer-Exford conditions that one finds when you do a mechanized proof from Coq.
And how did that relate to BGP and its access?
I don't. My experience is similar to Tim's. Every vendor has deviates from the spec and no games.
We did the TCP was, young, naive, and stupid, and even with quite a lot of effort, it was only just possible. BGP, I get the impression, is a whole lot worse over the years.
No, the thing about BGP is that, actually the protocol is pretty simple. It's the use that people put it to that makes things complicated, because it's like I said, you can have 1,000 lines of config file on a BGP. By the way, this is actually not the model that I work in mostly these days. I work in a model that looks like this. Routes, let's say, labels on links, something that takes the best guys, and a function like that, that's, let's say this function goes from labels to transformations on, these are the things that you put on a link. They're like, think of these as programs that there's a little program, this is my interpreter, and I given a root, I munge on it and give you back another root, okay? Again, we can have a distributivity rule that says something like, where am I? Oh, okay. So something like that, which, your protocol, your algebra may or may not satisfy. So BGP does not satisfy these things, but other things may. And this is a lot easier to work with because, when I'm talking about 1,000 lines of config file, that's what the label is, okay? That label is encoding that program that munges on route. It's typically a conditional thing. If the route looks like this, then do that to it. If it has that tag in it, do this to it, and so on. Okay, so I just want to mention before I forget, because Ewan Harris is here. He did a PhD. What year did you finish that? 2008. Again, I didn't entirely give up on BGP modeling, and we did Ewan's thesis was about a particular mechanism in the BGP protocol for rate limiting to try to reduce the number of, because if BGP is just naively implemented, you can easily get an exponential number of updates flying around and basically take down the network with update storms. So BGP has a rate limiting mechanism, actually, and you can think of several different ways to implement that, to sort of hold on to information a little bit and then kind of semantically collapse it while you're holding on to it. So for example, if a route goes announce, withdraw, announce, withdraw, announce, withdraw, you just say announce or withdraw at the end, or nothing, or you say nothing because nothing has changed. And Ewan implemented 2 different ways to do that and compared them and did a bunch of simulation and stuff. So very nice work. So I didn't entirely give up on BGP specific stuff, but I've been trying to do more general stuff that can be applicable outside of networking. Okay, so very briefly, I'm just going to talk about some of the stuff.
Is the preference ordering part of the structure too, or do you think that's coming outside?
That's, the ordering is there. So the ordering is there. Why? Because usually you define something like A is less than or equal to B, is A is equal to A plus B. So that's the ordering that it's implicit in that plus, okay? Sometimes it's a partial order, sometimes it's a total order. When you're using something like Dijkstra, it has to be a total order. And other protocols or other algorithms like Bellman-Ford or Warshall's algorithm are a little bit more liberal. They can handle partial orders. But Dijkstra, because of the way Dijkstra works, you really need a total order. So here's an interesting thing that we discovered. So you asked me about the transition. Why did I abandon, I mean, not completely, but why did I move from doing this kind of stuff to more sort of traditional algebra and these kind of structures? Because at about 2005, João Sobrinho from Portugal did some work on saying, I mean, because, we knew about semi-rings and stuff, but we knew that this wasn't working, right? This didn't work, so we didn't pursue the semi-ring world. And João said, well, just give up on that. Just admit we're working in this framework, but hey, this might not be true. So let's see what we can do there. Okay. So which is weird. If you talk to mathematicians, semi-rings are already so impoverished that they're just not interested. typically. Go to the math library over there and see that the shelves are creaking with books on ring theory, and there's like one book on semi-rings. Semi-rings are used by engineers, right? They're used by computer scientists, electrical engineers, and other optimization. It's a Gondran and Minot who wrote the sort of Bible on semi-rings. They're operations research people. Okay, that community knows about these things. Okay, so João did this work, and that's sort of why I've kind of moved toward the algebraic thing, because I think I want to tell this story, right? That we don't want to give up on semi-rings. We want to sort of extend that theory, and we want to make it applicable in areas outside of networking. So one of the first things that João and I did was we wanted to come up with an algorithm that would solve these problems. Oh, by the way, let me put it another way. Suppose I have an adjacency matrix, okay? And I want to solve this equation. Okay? So I can think of this mapping. These are matrices. And this maps some values to nodes in the network. This is just an n by n matrix, okay? And this is the adjacency matrix. I'm thinking in the semi-ring world now, okay? And if the semi-ring has certain properties, then you can just iterate this equation, which looks a lot like Bellman-Ford, and you come up with A star, which is A star ij is equal to the sum over all paths from, I'll just say paths from I to j of the weight of the path. Okay? That's what you get when you iterate. If the semi-ring has certain properties, essentially this property, that you will get this A star, which is, it's going to be essentially the solution is the best path, the weights of the best path, right? There's also another way to look at this. There's that equation, okay? So A star solves the equation. So essentially what we've done with our extended work is to show that when this is true, but this is not, then we still solve this equation. It's just not that solution. It's a different solution. In other words, when you throw away distributivity, this rule, then you can get two different kinds of solutions. I call this a global optima, and I'll call this a local optima. This is exactly what the picture you're seeing here. Everybody gets the best thing they get given what their neighbors have in a stable state, okay? So and then we have a right version of this equation as well. I'll just say a right version is equal to x times a plus m.
R type thing?
Yeah, thank you. I should have put L in there for x for the left version. So this is Bellman-Ford essentially, or distributed Bellman-Ford, and this is Dijkstra. Dijkstra solves this equation one row at a time. Because basically you grow the tree and you add things, and so you're looking at a different picture. So Dijkstra solves that equation one row at a time. And again, what was really surprising is João and I discovered in about 2009-ish, and I think it was published in 2010, that Dijkstra, if this holds and distributivity does not hold, Dijkstra still solves this equation. Gives us a local optima, which has really surprised us both, because I always think of Dijkstra's algorithm as being extremely fragile. You can't change it at all without breaking it. But we were both surprised. The traditional proof that you see in the algorithm books is pretty straightforward, based on basically the fact that subpaths of shortest paths are shortest paths. That's really what the proof is, right? It's no longer true with this. And so the proof of this is combinatorial in a way that's kind of messy. You essentially have to come up with a whole bunch of invariants and make sure that they're maintained at each iteration of Dijkstra's algorithm. That was kind of fun. Let's see, where are we going now? Okay. There's a whole bunch of work that I'm not going to talk about that I did with Matthew Daggett, and we're still publishing stuff from his dissertation from 2018. And what he did was he looked at asynchronous convergence of these kind of exotic algebras. Because we were thinking, okay, you iterate this equation, okay, that's fine, you know, sort of a static thing. You have all knowledge and just iterate matrix multiplication. Well, maybe in an asynchronous world, something can go wrong here that doesn't go wrong in the semi-ring world. And so he built in Agda a model of asynchronous computation here. There's a theory, a fixed point theory by Ursulin and Dubois that we generalized and used it to prove that, again, using assumptions like this one, that this abstract model of an algebra like this will converge asynchronously, okay? So that stuff is really technical, and so I'm not gonna talk about it so much but I just want you to know that it's out there. Now, another thing, if your algebra is nice like this, and you have a semi-ring, and you iterate this equation, it's well known that you need at most n-1 iterations. Okay, essentially n, where n is the number of nodes in the network. It's a standard semi-ring thing, right? So what we wanted to know is when you're in these, you know, by the way, we could replace that times by one of these guys, right? And it's pretty clear. By the way, what is multiplication on matrices is just exactly like the ring theoretic multiplication. You just use plus and times. You know, you raise, it's some sort of convolution. So you can do the same with that diamond. And, you know, the question is with these exotic algebras, how many times we know it will converge, we have proofs that it will converge, but how many iterations does it take? You know, I'm just talking about, you know, just matrix iterations, how many times? And there were lots of conjectures about it, and it was kind of an open problem for a long time, and we solved it in 2018. It turns out, whereas with semi-rings, it's order n iterations, with our exotic guys, it's order n squared. Now, there's something I haven't told you, is that when we have these exotic guys, these exotic algebras, the algebra itself has to contain a path, right? And you have to throw away paths that have loops in them. The same is true for shortest paths. So shortest path, the very first routing protocol was called RIP, R-I-P, Routing Information Protocol. It was a distributed Bellman forward. You listen to your neighbors, you believe them, you just keep iterating the matrix equation, but it didn't have paths. So what can happen is you can fool your neighbor. There can actually be a loop in the network, and you don't see it because there's no path. And so you can do what's called counting to infinity. You know, see, the best path has length 1. Oh, the best path has length 2. Oh, no, it's 3, it's 4, it's 5. And so RIP's solution is infinity is equal to 16. Okay? This is when networks are really small. And, you know, it seemed okay. You know, who would want a 16-hop network in the original internet? You know, so infinity was 16. BGP solved this problem by putting a path in this guy, S, each element there contains a path. And you throw away things that have a loop in them, okay? So you need that even if you're using shortest path, okay?
Do you put that in this framework?
You include it in the algebra. I'm not going, okay, I'll talk about it, but when I talk about meta-routing, I'll talk about how, Peter, feel free to tell me I'm out of time.
Forward dating, but now it's 12:25.
Yeah. Okay, I'll try to finish soon then.
I have not tested the interpreter running for months.
Can I go to,
How about you give me more minutes, like 16 more minutes?
I'll try to wrap up as soon as possible. But the thing about these, so with Bellman-Ford, with shortest path, right, with this path in there, if you added paths to RIP, for example, you would never get this confusion situation, right, where you're lying about things. But when you go to the exotic algebras that this is not true, you can have nodes fooling each other again, because distributivity is violated. So the reason we get n squared here is you have to flush that information out of the network. How long does it take to flush all of the stale paths out of the network, basically? And that's why it's n squared in the worst case. No, what? This is a protocol that's running on its own, right? It's just so you really have to work hard to get an example that takes n squared. You really have to work at it. So I doubt that in practice that happens a lot. By the way, we don't have to even go to strange things to see this thing violated. It's like if you have an algebra, so A, B here, and then a path I'll just say PI for path information. So if this guy is shortest path and this guy is max min, so widest path, perfectly nice semi-ring. If you switch this guy, in other words, you say, I'll say I want the most priority, I'll give capacity the highest priority, and then I'll break ties on path length, and then I'll do, this bit is a semi-ring, perfectly good semi-ring. This thing together is not. Okay, so we didn't need exotic policy. We didn't need some weird exotic policy language to break distributivity. And you can find people describing these kind of things and not realizing that actually, and why is it? It turns out for lexicographic product to work properly, this algebra has to be cancellative. You know, A times B equals A times C implies B is equal to C, okay? And that's not true when you have something like max min in there, okay? So the upshot is that, you know, this converges fine, it's just that you don't get all the paths you think you're gonna get. There are paths you don't get because you're not getting a global optima. You're getting a local optima. Okay, so what I'm going to talk about now is this other project that started in 2005 that I'm still working on today. And it was called Metarouting. I don't think that was a good name. I've always been kind of thinking that that was a bad name to give this thing. But the basic idea is that building, so even in the semi-ring world, if you read the literature that's out there in the operations research world, for example, there are very complicated semi-rings that people define to do things. For example, there's a semi-ring that if you label each guy, with the set, containing the set, this is ij, and you have ij in there. So this is the set of links, the set of links, right? Okay, you start this is your original configuration, your A, and you turn the crank. I'm not going to describe the plus and times here. What do you get for ij? You get the set of all minimal cut sets that separate I and j. Okay? This is a complicated semi-ring, right? Really interesting. But when you look at these complicated semi-rings in the literature, you know, people spend an enormous time proving that it actually is a semi-ring, okay? Or it has certain properties and this and that. And then you look at another semi-ring and you see, oh, there's parts of that proof are the same as this other guy, right? And So the idea is, in this meta-routing idea, which is, again, a bad name, is to come up with a language for combinators where I automatically, you sort of look at all these proofs, abstract away from what's going on, come up with really simple algebraic structures, you know the properties of these things, and then every combinator knows how to construct proofs from the proofs of its arguments, okay? And so every property you care about is decidable, okay? In other words, is it distributive or not? Or is this property true? They're all decidable for every algebra you can define in this language. And that's the language I've been working on and implementing it in Coq. And I'm still working on it. And after talking with Nate yesterday, he convinced me that I really should push it out into the public as soon as possible. And I'll try to do that. But there are lots of surprises there. I think I'm out of time. There are lots of surprises there, and I won't go into it now. We're out of time, basically. But again, I have been working on the control plane stuff here. Nate has talked about the data plane. I have thought a little bit about unifying things, but I went down a different route. I sort of looked at a bunch of work going on today in the ITF and in the vendor space called segment routing. And it seems like a really interesting thing where they've actually integrated forwarding information with routing in a really tight way. And I thought that abstracting away from that, this is work in progress, by the way, abstracting away from that would try to get at trying to unify these two different theoretical frameworks. And that segment routing and modeling that involves putting a stack on every packet, just like Nate was talking about. So Nate, we have to work on this. We have to figure out what's going on here. Because somehow this idea of adding stacks is there in segment routing as well. But again, it's coming from a different direction, not from a Dexter-Cozen direction, but more from a Cisco direction. And the two will meet someday, we hope. Okay, questions? Yeah.
If you define let's say, will be like this, and you don't have distributivity, that also means that you do not have a kind of a congruence reasoning. So if you take this A less or equal to B, multiply it by K on both sides, you do not know what you have.
Well, not necessarily, but sometimes you do still have this. That's all that matters.
You don't care about this kind of reason.
Yeah. So I'm interested in this. By the way, when you go to the exotic stuff, I should have been honest with you. I've got to do that. Okay. I have to say strictly less than. Sorry. With Dijkstra, Dijkstra's happy with that, but Bellman-Ford is not. It has to be a strict less than there, with a path that avoids loops. Okay. Because if we allow that, you can come up with counterexample. But this is natural, right? In the routing world, that's a perfectly natural thing. When you extend a path, it gets worse, right? It doesn't get better, it doesn't stay the same, it gets worse. So that's not such a unrealistic assumption, I think.
Scared that
Thank you.